Bismillahirrahmanirrahim. This video will be solving end chapter question 6.31 from Mr. Nilson's book. And this chapter deals with the inductance, capacitance, and mutual inductance. And this is on the request of a student named Rowan, Rowan. So this before starting the question, let's see one or two points. First part of the question says the two series connected capacitors in figure are connected to terminal of a black box at t is equal to 0. So this is a black box. It's a load actually, and we have two capacitors here. The capacitors are charged beforehand. The switch is actually not closed. It is opened when the capacitor is charged, or the charged capacitor are connected here. The resultant current IT for t greater than 0 is 800 e raised to the power minus 25t. Now to show how will this current look, I have just taken help of MATLAB, and I have just written a small program to show the shape of the current as the time passes by. So you can see the current is starting from 800 microampere, and then gradually it is diminishing, decreasing. That means the capacitor, which was fully charged, will gradually dissipate through the black box. And ultimately, at infinity, this will become 0. Okay, now let's read the whole question. So this part, the first part we have to find, replace the original capacitors with an equivalent capacitor and find V0t. So we have to replace this capacitor, and then we have to find V0 at time t. The next part is find V1t, find V2t. Now when it says t, that means after t is 0 or t greater than equal to 0. Then how much energy is delivered to the black box? So the energy consumed by the black box or delivered from the capacitor to the black box from this time interval. How much energy was initially stored in the series capacitor? So energy is stored in the capacitor. How much energy is trapped in the ideal capacitor? So energy trapped means energy left over after it has been consumed by the black box. And then we have to show the solution of V1 and V2 agrees with whatever energy trapped we find here. So we'll go step by step. First part first. First we find the equivalent capacitor. So I hope you know by now that the capacitors in series are treated as resistors in parallel. So we solve them in, like resistors in parallel. And since there are two capacitors, so we'll be using this formula. And for two resistors, we know that R1, R2 parallel is R equivalent R1 into R2 divided by R1 plus R2. So we'll use the same formula for the capacitor. So C equivalent will be the multiplication of the two capacitors and addition of the two capacitors. And the answer after solving will be 1.6 microfarad. So we can replace these two capacitors by 1.6 microfarad capacitor. This is the first part. We found the equivalent capacitor. Next part is find V0t. So find V0t for t greater than 0. Now this is after the switch is closed. Then we have to find V0t for any time t. And voltage across the capacitor for any time t is given by this formula. 1 over C, 0 to t integral IT plus a constant which is the initial voltage, initial capacitor voltage. And now this was our circuit. We had opened, the switch was open for t less than equal to 0. The capacitor was charged. And this voltage we'll call V00, the initial voltage. And so here also these two, actually this is V10, V20, and the sum of this will be VO0, which is this one, VO0, same as here. Now, how much is VO0? The easiest way is to take a KVL. So from here, plus V0 minus 5 and plus 25. V0 minus 5 plus 25. And from here, we can calculate V0 to be minus 20. So keep this in mind that this voltage, the initial voltage for the two capacitors now is minus 20 volt. The current is given, initial voltage we have found. We'll now apply the formula. Equivalent capacitor we have found 1.6, so we use that. This is the current, and V0 is minus 20, so we write minus 20 or plus V0, so minus 20. And then simple integration. We take out all the constants, so we just need to integrate e raised to the power minus 25 tau d tau. Integrating this or solving this, we get 500. Integrating the e raised to the power minus 25t is e raised to the power minus 25t divided by this constant minus 25, and then we put the limit from 0 to t, and also we write this 20. So solving or this further dividing will give you minus 20. So e raised to the power minus 25 tau and the limit 0 to t. Now we'll plug in the value of the limit t in the first case and 0 in the second case. We know e raised to the power 0 is equal to 1. So our answer will be this part, then this will be 1 minus 20 and minus 1, so plus 20 and this minus 20. And solving these two cut, then minus 20 e raised to the power minus 20t is the voltage. So this is VOT. At any time t, this is the voltage. Anytime t greater than 0, of course, greater than equal to 0. So part A we have done. Now part B is V1t. So we just use the same formula. In this case, we just V1t will be 1 over C1. So this we are calling C1, and then we have to find V1. Now V1 again, from here you can see this is the voltage for V1. So it is better that you follow KVL, so we'll have no chance of making mistake about the sign. So plus V1 minus 5 is equal to 0. So V1 is equal to plus 5. So here now we'll place plus 5 and putting the value of the capacitor, 2 microfarad, the current and the 0 value or the constant voltage, and solving as we did in the previous example. I hope you can follow this. This will be minus 16 minus minus plus, so plus 16 and plus 5. And so the answer will be minus 16 e raised to the power minus 25t plus 21 volt. So V1t we have found. Exactly similar, we'll find V2t. I will not write this equation. You can write it for V to T. Just plugged in the value 1 over C. Now in this case, C is 8 microfarads. We have used this current, and this was the integral value with the limit. Now V0, this one V20. Again, we'll take KVL from here. Plus V2 plus 25 plus V2 plus 25. That means V2 in this case is minus 25. So we'll write minus 25 for this value. And solving, this is our answer for B2T. So part C done. Now part D is how much energy is delivered to the black box in time 0 to infinity. So energy delivered to the black box, we have to find out. And we know the formula for energy. There are two formulas actually. Half CV square is for the DC values. And when we have variable values or in the transient mode, then we use the integral formula. Integral of power is energy. And now what power should be right, plus or minus? Some students get confused. So in one of my videos, I had just put in this picture. You can see the father is delivering the money to the son who is studying in the university. The father has gone broke or negative. So delivering, power supplying is negative. So we write negative sign with the power supply. And he is absorbing the money or getting the money. So we will have the positive sign. So you can remember it like this. Now in our case, it is saying power delivered, therefore we'll use the negative sign. So power delivered will be negative voltage into current. And this was the total voltage that we had found. And the current, already we know this was the current. So plugging in the two and solving, we get this value. And now we'll integrate to find the energy. This was the power. Now energy will integrate from 0 to infinity. Y0 to infinity, here it is says T0 to T. But in our question, it is saying that we calculate from 0 to infinity. So we put the limit from 0 to infinity. And this was the power. So integrate. And I hope by now you are familiar. This is the value and the limit, plugging in the limit. And some students get confused about the value of e raised to the power minus infinity. I've just shown it here. E raised to the power minus infinity can be written as 1 over e raised to the power plus infinity. And anything power infinity will be infinity, so it is infinity. And 1 divided by infinity or anything divided by infinity will be 0. So this term, the first term will be 0. This is 0. E raised to the power 0 we know is 1. And solving, our energy will be 0.32 millijoules or 320 microjoules. Okay, coming to question E, how much energy was initially stored in the series capacitor? So energy stored will be calculated for each capacitor separately. We'll use this formula because these are the DC values. And just plugging in the values, C here is 2 micro, and the voltage was 5, so 5 square. In the second case, 8 micro, and the voltage was 25, so 25 square. And solving, we found the total energy stored in the capacitor is 2525 microjoules. Now, the how much energy is trapped inside the capacitor. So energy trapped in the capacitor will be energy stored in the capacitor minus energy delivered to the load. We know both of these values, that is energy initially stored minus energy delivered. We had calculated this initially stored. We had also calculated in step D the energy delivered. So this much is trapped in the capacitor. And finally, part G, show that the solution for V1 and V2 agree with the answer of F. So this value. For that, what we'll do, we'll take both the equations, write both the equations, and use this formula. Now here, this is the DC part only. Similarly, in this case, it is minus 21 is the DC part. So we'll use these two values. So half value of the capacitor, the first capacitor, and this is the voltage. In the second part, value of the second capacitor, and this is the voltage. And solving, we find it to be 2205 microjoules. So it is the same answer that we found in step F. And therefore, the finding or the values of V1, V2 agree with the result of F. I hope you have been able to follow this. Please let me know through your comments. Thank you.